and Lagrangian in the unregularized space of waters. But we will look a little bit about the importance of the rank 2 case. So just to establish notation, I will work with C, a smooth projective curve and creating the canonical. In and we are homomorphic rank I vector bundle over C. And for a Higgs bundle, I will denote E and psi. And homomorphic Higgs bundle, and what we mean by this is an orbital matrix of homomorphic differential. For connection, we will use notation V and nabla, and it satisfies the Leibniz rule. And these are two examples in rank 2. So we're going to use, in particular, the first one that we were going to denote by the heating section, maybe any quadratic differential, choose any quadratic differential on the base, and this will give us an example of a Higgs bundle. So what is important is that any connection locally on the curve C can be realized as exterior differentials of A, where A is a general matrix of forms. However, it's very different than a Higgs field, and mainly we satisfy different rules with respect to transition functions. So if F and G are the transition functions for the vector bundle C and G respectively, then the Higgs bundle is compatible with the transition functions, while A satisfies the gauge transformation. So in particular, it's not obvious if we start from a Higgs pair, how to end up with a connection, or reversely. So this is what we're going to see in this talk, how to construct such a correspondence in a particular case. And then we remind the motivation of what happens in rank 2 Higgs bundles. This is what we mean by quantization theorem. So with Motoshiko last time, we did work around the topological recurrent formalism, and we discovered that the good perspective is in the heating context. So we use the same notation, but phi in this case to have possibly holomorphic entries. So in 2013, we discussed the case when phi is a holomorphic Higgs field, and we use the spectral curve constructed by heating inside the co-tangent of C. The year after, we discussed the monomorphic case, and we constructed the spectral curve inside the compactified co-tangent, and we constructed the resolution of singularities by blowing up distributed surface. And what we discovered, the quantization theorem in rank 2 is that when it Higgs bundle in phi locally on C, so X denotes a parameter on C, there exists locally a second-order differential operator, P of X, H bar dx. The semi-classical limit recovers sigma, so once we know the spectral curve sigma, we get our hands on an explicit second-order differential operator, such that the second-order differential operator is the grading function of free energies. And then still on that for us, our motivation was to make a connection between apparently two different worlds, the chromometer theory and teaching theory, by running the topological recursion formalism, while in the holomorphic case, it constructs the limit operator of conjecture. We're going to see that. So all these examples that we know happen in the holomorphic case, and this is something we will take just for our main rank 2 example, here, recurse. So the base curve is P1, the vector bundle is half canonical plus half anti-canonical, and the holomorphic case is this, with holomorphic entries. The spectral curve inside the fixable surface is locally at the 0, chart given by the characteristic polynomial, so mainly y squared minus xk squared. While if we move the differential surface and if we move along all the charts, infinity, we find a quinticost. And mainly what we do is to blow up this spectral curve and resolve the singularity, and sigma tilde denotes the proper transform. And in this case, it becomes a rational curve. So what the topological recursion does for us, what the quantization theorem does for us, it finds the second-order differential operator, h bar squared dx squared over d over dx squared minus x. That's just the grading function of free energies. So this is the quantization part. The primary satisfier recursion, that's in the node, and this encodes the gamma-vision invariant of the point. We then have we were able to run two examples of the P1 of monomorphic Higgs of rank 2, in which we find connections with gamma-vision theory, or enumerative problems that we knew. So at that point, the question was that this at that point is not a globally defined operator, but it's local. So we need a way to make it globally defined, and for this we need a definition of projective coordinate system. So from now on, in order to discuss the conjecture, we will look at Higgs fields with holomorphic Higgs fields. So this first is the Riemann surface to have fields at least 2. And in theory, what we cover is the upper half plane. And this has a global coordinate at first, and the question now will induce a global coordinate on C. So this is the definition of Gunning in 67. A projective coordinate system on a Riemann surface is a coordinate system on which transition functions are given by Möbius transformation. And this is precisely what we mean by this. The connection between Z alpha and Z beta is done by a SL2R matrix. And in particular, on a projective coordinate system, the half canonical can be, transition functions of the half canonical are linear. And this is something that we will use in the proof of this. So the importance of Gunning definition is that on a projective coordinate system, the quantum curve given by the topological recursion is globally defined. So this will be our first definition of operators, and we'll come back to this from geometry definitions at the end of this talk. An operator now will be a globally defined differential operator. So in particular, the quantum curve, when we use simple case when h bar equals to 1, will be an operator from which we work on a projective coordinate system. And we can interpret globally a second-order differential operator as a system of first-order system of equations, so an operator acting on this vector. And in the early example, we started with this Higgs field, and this was the quantum curve. And this quantum curve in a projective coordinate system, it corresponds to a family of operator, not h bar, that is d plus 1 over h times this matrix. And this matrix looks like a Higgs field, but it will have a connection. So it is a connection, but what is the corresponding vector bundle for this family of connections? And the solution comes from